mental conditions, ultimately being overweight, which has its own problems associated with it, and so on. So here's the structure. It's essentially, it is a molecule of glucose and a molecule of fructose. And you notice the beauty of the linkage. The linkage is an ether linkage, as in fact all polysaccharides, their linkage is through the OH functions. And sucrose chooses a linkage at the anomeric carbon of glucose, the hemiacetal carbon of glucose, with the hemiacetal carbon of fructose. Yeah? If you rotate this around, you can see what happens. Both of these carbons are now protected. They're mutually protecting each other as full acetals by forming this oxygen bridge. And notice that the stereochemistry is completely defined. This OH is up in fructose, so it's the so-called beta OH, and this OH is down. So this is the axial OH in glucose. So if you're back to the hemiacetal carbon, this is the all-equatorial structure where the OH is up, equatorial, but it can also be down, okay, because this thing is in equilibrium with the open form, and you have a certain amount of OH down. In sucrose, it grabs the axial OH to make that linkage. And that linkage, of course, since it's an acetal linkage, is very susceptible to acidic hydrolysis already in your mouth. Actually, this thing hydrolyzes to glucose and fructose. So this is basically just a protected, non-reducing form. So this guy cannot be oxidized, and this presumably was chosen by nature to protect the structure from oxidation because the vulnerable hemiacetal carbon, which remember is in equilibrium with the aldehyde, it can't open. It's protected as the acetal. So if you go down to real polymers, okay, we got cellulose, and cellulose is a glucose polymer. It's just simply glucose polymerized. And notice that the polymerization is now at the hemiacetal carbon. That OH is now the equatorial OH, so it uses this stereoisomer, the so-called beta isomer, and it's linked to a second molecule of glucose at carbon 4, as indeed many of these oligomers use this carbon 4 OH. Which in this case is also equatorial, to make an ether bridge. So this is now basically dealing with this end of the second glucose molecule as an ordinary alcohol, capping off the hemiacetal carbon of glucose at the other end as an acetal. And then it just repeats itself over here, just keep on going. So cellulose has a molecular weight of about 500,000, 3,000 units of glucose, and every unit is about 178 molecular weight. And these polymers, because of hydrogen bondings to each other, these chains build up very rigid structures. They are responsible for cell wall material. Here's a magnified picture of cellulose. Wood is largely cellulose. Paper and cotton is pure cellulose. Okay, so when you look at paper now, the paper you write on, it's actually sugar that you're writing on. Okay? It's a polymer of glucose. And the beauty of this is also that if you change the stereochemistry of the polymer at this position, such that this connection now is alpha, that is, the OH is down, it's the axial OH, but it's the same polymer, it's an isomer of this polymer, you get starch. Okay? That's the starch in potatoes and spaghetti and bread and so on. That's also just a polymer of glucose. It just has a different stereochemistry at this carbon here. That carbon stays the same. And so there's since this is all glucose polymers, and they're just linked by a highly vulnerable to hydrolysis, acetal linkage, indeed, they all hydrolyze to glucose. And that's where the energy storage capability of these polymers comes from. And a good experiment for you to do, if you haven't done so actually inadvertently, is to take a piece of wood, or maybe better a piece of bread, and put it in your mouth and leave it there for a few minutes. And you will very quickly notice taste of intense sweet taste, okay, which may seem disgusting. Okay? But it's just the starch hydrolyzing to glucose and giving you the pure glucose sweetness. And that's sort of an experiment that drives home where we are. Okay, so much for sugars. Let's now talk some about heterocycles. This will be rather brief. It's a short chapter. A lot of it we already dealt with off and on in various sections of the book. We'll do a little bit of nomenclature, and the nomenclature is really, in a way, trivial. Heterocycles basically are defined as cyclic molecules or cycloalkanes, in which one or more of the carbons are heteroatoms. And they're named as cycloalkanes with a prefix that indicates the nature of the heteroatom. So if you have an oxygen, so that would be a cyclic ether, like tetrahydrofuran, it would be called an oxacycloalkane. So tetrahydrofuran really in IUPAC is oxacyclopentane. Okay? 5-membered ring, cyclopentane, one carbon replaced by oxygen. And with nitrogen, there's a prefix aza. With sulfur, there's thia. With phosphorus, there's phosphor. With plutonium, there's plutona, and so on. It's always the same. Okay? We'll focus primarily on oxygen, nitrogen, and sulfur. So if you look at the various ring forms, here's the simplest one in terms of the ethers. That's oxacyclopropane. We've seen that camper frequently. We've used it as an alkylating agent because nucleophiles attack a carbon and ring open it. When you have the corresponding nitrogen system, it's called an azacyclopropane. Now, since nitrogen is trivalent, there has to be another substituent here, and we specify this as we did in the case of amine nomenclature and amide with a prefix N followed by whatever the substituent is. So this is an N-methyl azacyclopropane. When you start having substituents in the ring, other than on the heteroatom in the case of azacycloalkanes, then by definition the heteroatom is atom 1. Okay, so it's labeled as 1. And so when you have a fluorine here, that would then be the 2 position, because you number, in this case, clockwise in order to give the first substituent the lowest locant. So it's 2-fluoro-thiacyclopropane. And 4-membered ring, that's oxacyclobutane. 6-membered ring, oxacyclohexane. At position 3, there's a methyl, so it's 3-methyl oxacyclohexane. If this is a stereochemically defined, wedged or dashed, you have to figure out RNS. So there's nothing new here, really, except for this prefix issue. Otherwise, it's like cycloalkane nomenclature. So 3-cyclopropyl, thiacyclohexane. I throw this one in where we have 2 heteroatoms, so then you just do it as a 1,3-dithiacyclohexane, this guy, because we use that as a system in which we can generate acyl anion equivalents by deprotonating here. But I won't do in the exams several heteroatoms, although it's simple extension, and you go alphabetical, and you number where they all are. But we'll just stick with one heteroatom. That's enough. Okay, so how do we prepare these? Nothing new here either. And we've done that in conjunction, particularly with SN2 chemistry, already starting in 3A, continuing in 3B. It's all SN2, intramolecular SN2. It started actually with the intramolecular Williamson ether synthesis in Chapter 9, where we look at the rules for ring closure, speed and strain and all that. All of this applies to all of these heterocycloalkanes. Okay? So this can be oxygen, as in the intramolecular Williamson ether synthesis, and intramolecular SN2. The rules for ring closure hold, namely, you have to worry about how sterically hindered this is. Okay, tertiary doesn't work, although there you can resort to SN1s, leaving group abilities, and inversion of configuration of that carbon if that carbon happens to be a stereocenter. But you basically displace and make the cyclic system that way. There was one exception. That was a special reaction that we applied, so it gives you an additional way of making oxocyclopropane, and that is the direct oxocyclopropanation of an alkene, and that goes back to Chapter 12. And for that, we used peroxycarboxylic acids, particularly R being trifluoromethyl, because that activates this oxygen here, makes it more blue. If you have trifluoromethyl here, it pulls, and by relay, it makes this oxygen more electrophilic. And the mechanism of this, I won't go into. You can look it up. It's Battle of Hastings mechanism. Everything happens all at once. And the oxygen is added, and it's added stereospecifically such that if you start with trans, you get the trans product. If you start with cis, you get the cis product. So that was the only additional way of making oxocyclopropanes. You can make oxocyclopropanes also by intramolecular Williamson ether synthesis. Okay, and we've used these guys only for synthesis really when you could do ring opening. And the ring opening is only possible for strained systems because these things are extremely stable. Okay? And the oxygen, nitrogen, and sulfur, and phosphorus, and so forth, per se, allows the leaving groups. So you need the ring strain to help you kick out these heteroatoms as leaving groups. And we've seen most of it with oxocyclopropanes, and synthetically most useful are basic conditions, that is, anionic nucleophiles attacking, rather than acidic conditions. There's a blurb in and I think we review this in this chapter, where acid-catalyzed opening, of course, is possible, but synthetically, most reactions, particularly those involving carbanions, like alkyl lithiums and Grignard reagents, and enolates that we've seen this semester, and we've applied them to oxocyclopropanes. They're all anionic, and those are straightforward SN2 ring opening reactions. Okay? Following the rules for SN2, namely attack occurs at the less hindered carbon. There is inversion of configuration if that carbon is chiral and non-numerically defined. And so methoxide, for example, will ring open this to this methoxy alcohol. 4-membered rings we've done less, but they will also ring open, not quite as readily because it's now a 4-membered ring, not quite as strained as a 3-membered ring. So if you open this with methylamine, which on top of it, of course, is a neutral nucleophile, you need to heat this up quite a bit. And the yields aren't that great here either. So typically, most of these reactions we did for oxocyclopropanes, but 4-membered ring compounds will open if you push the issue. Once the rings get larger, such as tetrahydrofuran or oxocyclopentane would be the correct name, or azacyclopentane or thiocyclopentane. These guys are really stable. Very difficult to ring open them. The conditions are typically those that are used for normal ethers, alkoxyalkanes, really quite drastic. You need strong mineral acid where you have a counterion that is also a good nucleophile. That really, as far as we're concerned, means HBr or HI. And then indeed protonation is followed by nucleophile attacking and kicking out the protonated alkoxy as the alcohol. And so you can ring open, and under these conditions, of course, this alcohol that you get is equally susceptible to protonation and bromide doing an SN2. So in the end, you get the dibromide. Synthetically, not great because these are conditions where almost every other functional group, think of acetals, think of esters, think of amides, a lot of the functions that we've discussed this semester, they will all react. Okay, so there's a lot of competition. And this is, of course, the reason why ethers are used as solvents in Grignard reactions and enolate reactions and alkyl lithiums and so forth, because they don't do anything. Okay? That's the ideal solvent. And so we won't do anything with them either. But the strained ones are okay. So the most interesting ones in this series are not the saturated ones that we've covered pretty much, but the unsaturated systems, particularly the so-called heterocyclopentadienes, where you have cyclopentadiene and you've replaced the CH2 group in cyclopentadiene with a heteroatom. And the reason for that is that they are aromatic. How come? Well, you just count up the electrons. So if you have a diene system like that, and you're capping off the two ends of the butadiene with a heteroatom that has an electron pair, this electron pair will start communicating with the other 4 electrons. And if you count it up, that's 6 electrons in a cyclic array. That's perfect. 4n plus 2. It's isoelectronic with benzene. 6 electrons. Okay? In order to maximize this overlap, this nitrogen, and in the case of the oxocyclopentadiene, the oxygen, the sulfur, same thing with the sulfur, they rehybridize so that this lone pair, they rehybridize to sp2, so that the lone pair is sitting in a p orbital. Okay? So it's a p orbital with 2 electrons in it, perfectly aligned with the diene array here. Because these are so special because of their aromaticity, and obviously they have a long history because they're relatively stable, so they were isolated from nature very early in organic chemistry, IUPAC retains their common name. So rather than calling this aza-2,4-cyclopentadiene, oxa-2,4-cyclopentadiene, thia-2,4-cyclopentadiene, the nitrogen one is called pyrrole, this one's called furan, that's where tetrahydrofuran comes from, the ether solvent, and the sulfur one is called thiophene. And one can see this very clearly if you make a molecular model, and the analogy is the fact that these guys are also all isoelectronic with cyclopentadienyl anion. So it relates back to the fact in cyclopentadienyl anion, too, starting from cyclopentadiene, we pull an electron away, we leave an anion behind, an alloanion, and this electron pair starts delocalizing around the ring. And you get a structure like this, a perfectly symmetrical structure where we have 5 carbons, 5 p orbitals interacting with 6 electrons stuffed into them. Okay? And the way we show this with resonance structures is to show, say, the backbone here, 4 of these orbitals making 2 double bonds, and the 5th one has 2 electrons in it. But this is just one resonance form. Okay? There are 5 of those. And so a better way to look at this is that this is a symmetrical system with the negative charge delocalized over the 5 carbons, 1/5 of a negative charge on each carbon. When you turn to pyrrole, you actually get essentially, in a molecular model scenario, the same model. Okay? Now you have to imagine that the carbon I'm holding with my right hand is actually a nitrogen. Okay? And here's the hydrogen on that nitrogen. But that nitrogen, instead of being sp3 hybridized in a normal amine, it's sp2 hybridized. So that the two electrons, the lone pair on that nitrogen, wind up in a p orbital that can overlap with the diene systems. And if you turn to oxygen and sulfur, they're divalent, so they don't have a bond down here, no hydrogen here. It's just the second lone pair. But notice the two lone pairs are differentiated such that one of them is in a p orbital, and that it overlaps with the other four p orbitals to make the 6-electron aromatic array. And the second one is perpendicular to it, and it has nothing to do with this pi system, and it contains the second electron pair. Okay? So now the two electron pairs, the two lone pairs on oxygen and sulfur that we have always assumed to be equal, okay, they're actually quite different in terms of hybridization. One is involved in the pi system to give you the aromatic structure, one isn't. So if you look at the electrostatic potential map, cyclopentadienyl anion, all the charge is equally distributed. Once you go to, say, pyrrole, I'm just doing pyrrole here, you can see that it's all red, but the red is slightly displaced up to the top because this lone pair is donated like an enamine, like a double enamine. This electron pair is donated into the diene, and that shifts electron density. It makes the electron density distribution slightly unequal. Obviously, that's what you expect. It's an unsymmetrical system, whereas this is symmetrical, completely symmetrical. And these guys look pretty much the same as that. So here's another rendition of my molecular models. You can see here the hybridization, sp2 hybridized. So the lone pair is sitting in the p orbital, and it's doing its thing for aromaticity, and the NH bond, of course, is perpendicular. And when you replace nitrogen with oxygen and sulfur, then this bond, which is a 2-electron bond to hydrogen, sulfur and oxygen doesn't need a hydrogen because they're divalent, they're to the right of nitrogen, and so this electron pair now is just dangling in the so-called lone pair, and it's perpendicular to the pi system. You can do this all with resonance form. So we can do this, I'm doing it just for pyrrole. You can do it for furan and thiophene. You invoke delocalization of this electron pair by pushing it around in a sort of enamine structural electron pushing. And that gives you dipolar structures. Okay? So if you take this electron pair and arbitrarily move 3 electron pairs, you could have just moved this one here and that one here. But I'm moving all 3. That puts the negative charge over here to the left, and you get a positive charge of nitrogen. You can then do this again arbitrarily. I'm doing an allylic anion transposition where this electron pair moves over here, and this double bond moves over here. And so you get that. And then you can move again, this electron pair in here, this one here, that gives you that one, and then again 6 electrons gives you that one. Whichever way you do it, in the end, you have 5 resonance structures. One is charge neutral, and 4 others that have a negative charge on each one of those carbons. Okay? And that's just by way of pointing out that the negative charge is distributed over all of these carbons. So the bottom line of that is that the electron pair donates itself to the diene unit, making it relatively electron-rich, as you would expect. That lone pair is like an enamine. Okay? Makes these electron-rich, and that, as it turns out, translates into reactivity in electrophilic aromatic substitution. These guys, pyrrole, furan, thiophene, and the phosphorus analogs and so forth, they are highly electron-rich relative to benzene, and so they're much more reactive in electrophilic aromatic substitution, such that, for example, halogenation, you don't need a catalyst anymore. So they are as reactive as, say, phenols and benzeneamines. Okay? So how do we make them? Let's have a break.